Good day to everyone joining us, and welcome to today's X Talks webinar. Today's talk is entitled Wurster Fluid Bed Coating, Importance of Processing and Formulation for Success in Oral Pharmaceutical Delivery. My name is Sonia Hunt, and it's my pleasure to be your X Talks moderator for today. Today's webinar will run for approximately 60 minutes. This presentation includes a Q&A session with our speakers. This webinar is designed to be interactive, and webinars work best when you're involved. So please feel free to submit questions and comments for our speakers throughout the presentation using the questions chat box, and we'll try to attend to your questions during the Q&A session. Now, this chat box is located in the control panel, and that's found on the right-hand side of your screen. If you require assistance, please contact me at any time by sending me a message using that chat panel. At this time, all participants are in listen-only mode. Please note that this event will be recorded and made available to you for future streaming on xtalks.com. At this point, I'd like to thank Coding Place who developed the content for this presentation. Coding Place, founded in 1976, has over 45 years of experience in the pharmaceutical CDMO industry. They have advanced the design of their Wurster coating units by developing proprietary fluidization plates and nozzles. This technology, along with feasibility studies, linear scalability, and product development services, enables Coding Place to provide customers with the highest quality services available in the Wurster fluid bed coating industry. Now, it's my pleasure to introduce you to your speakers for today's webinar. And first, I'd like to introduce you to Charles R. Frey. He is the Vice President of Scientific Affairs with Coding Place, Inc. Chuck joined Coding Place in 1999. Since joining CPI, he has been intimately involved with Wurster fluid bed coating formulation development, process optimization, scale-up validation, and commercial production. He has lectured on fluid bed coating at many workshops and short courses through the Controlled Release Society, Bioencapsulation Research Group, and the Center for Professional Advancement, and contributed several book chapters on fluid bed coating and its application in pharmaceuticals and foods. Now it's my pleasure to introduce you to your second speaker, and he is Jared McDonald. He has 18 years of microencapsulation experience, including analytical, technical, and management positions. He is currently the Director of Formulation Development at Coding Place, Inc., CPI, where he oversees research and development, including formulating, design of experiments, technical transfer, scale-up, and statistical process control to best suit the needs of CPI's clients for pharmaceutical, nutritional, food, and industrial products. He has a BS in chemistry from the University of Wisconsin, Stevens Point. Now, before I pass over the mic and the controls to our first speaker, who is Chuck, we have a poll question for our audience members to interact with in real time, and that's appearing on your screen right now. And there it is. Now, this is done in, I'll give you about 45 seconds to complete this poll question. And once the poll question is done, I'll be able to share the results with you. So your participation is strongly encouraged and very much appreciated. Okay, so the question that we have for you is, rate your knowledge and understanding of Wurster bottom spray fluid bed coating. So we have a couple for you to choose from: beginner, a few years of experience, or significant experience. Okay, that looks like we have the majority of our audience members have cast their votes. So thank you very much, everyone. And for those of you who have not, please go ahead and do so now. I'll give you a couple more seconds, and then I will close the polls and share the results, and then go on to our second poll question. Okay, perfect. Thank you, everyone, for participating. Now, here are the results of that poll question. And the question was, rate your knowledge and understanding of Wurster bottom spray fluid bed coating. And the results are here. We have 63% saying beginners, 19% a few years of experience, and then 19% again for significant experience. So thank you, everyone, for participating in that that first poll question. Now I'm going to launch the second poll question, and that should be appearing on your screen right now. And there it is. And just like before, it's going to be done in real time, so your participation is strongly encouraged and appreciated. And I'll give about 45 seconds to complete this poll question. And the question is, what do you hope to gain from this webinar? So you have a couple of options to select from below: better understanding of Wurster fluid bed coating process, formulation strategies, insight on Coding Place's knowledge of Wurster coating, or other. So please go ahead and cast your votes now. Okay, that looks like we have the majority of everyone. A few more seconds I will give for those of you who have not cast your vote. Okay, that looks like it's the majority of everyone. So thank you everyone for participating. Now I'm going to close the polls and share the results. Okay, so the question was, what do you hope to gain from this webinar? And here are the results. We have 53% saying better understanding of Wurster fluid bed coating and process, 26% at formulation strategies, 11% for insight on coating places knowledge of Wurst coating, and again, a tie for 11% for other. So thank you everyone for participating in that last poll question. Now, I'm going to pass over the mic and the controls over to Chuck. So Chuck, when you're ready, you may begin.
Hello, everyone. And thank you, Sonia. And thank you all for being here. At Coating Place, as you've heard so far, we've been involved in Wurster fluid bed coating throughout our history. And we feel it's our strength and knowledge of the process coupled with our formulation expertise. It really gives us an edge and a success in oral pharmaceutical delivery. And clients have often asked us to share some of this, and so that's what we're attempting to do here in the seminar today. So we'll be looking at two things. First, the Wurster bottom spray fluid bed process. I notice that many have some experience, many are looking to learn more about it, so it doesn't really change what I'll offer here today, but hopefully give you some insight on how this works. Brief historical perspective of Coating Place and our involvement in Wurster processing. Get into the guts of the process, the fluidization principles and the scaling, going from one scale to the next. And we'll also look at spray parameters, which is the other heart of this process. After I finish, Jared will talk about formulation strategies and look at code layering and the ability to manipulate release patterns and things, and look at extended, delayed, and enteric coatings and how they can be manipulated. And then he will finish, I believe, talking about ion resin complexes. So Wurster coating history. The Wurster coating patents date back to 1953 to 1966. Dr. Wurster was originally working on coating tablets, and he has a couple of patents, one in 1953 and one in 1957, that were geared toward that. But by the mid-1960s, really found the forte of this process was in either granulating or coating individual particles. And that's the heart of what we do here. From 1966 to 76, the process was commercialized through the Wisconsin Alumni Research Foundation, WARF Coating Labs, by Harlan Hall and Ralph Pondell. And in 1976, the university decided they had taken this technology as far as they wanted to go with it, and they offered it to Pondell and Hall. Between Christmas and New Year's of 1976, they officially became Coating Place Incorporated. But it's this depth of experience going back into the actual patent work that CPI has, since we have all of the IP from the university. And CPI was actually involved in transferring this technology to GLAT Air Techniques. Many of you are probably familiar with GLAT coaters. But we have also been intimately involved with integrating other compatible technologies with the Wurster process. So just to put us all on the same page, I'm going to start out looking at the Wurster process. On the left, we have a diagram of a unit. There's basically air intake at the bottom of the unit, and basically air is drawn through the coating unit and goes out through the exhaust at the top. It's basically just a tube that's been bumped out in ways to create what we need to accomplish here. So the coating chamber is located at the base. There's a fluidization plate at the bottom of that. Particulate material is loaded into the chamber. Air is then drawn through that particle bed, and it induces a circular motion of the particles past a spray nozzle that's located at the bottom of the unit. Thus, bottom spray fluid bed coating. Particles are basically contained in the unit by a screen that sits on top of the fluidization plate and by filters that are near the exhaust point in the process. Filters are generally pulsed or shaken in some way to keep them from blinding from the particulate that they are containing in the process. So if we expand that coating chamber out to the right, we see a little more detail about what's going on there. And this is the heart of it, and this is sometimes what gets overlooked on the importance of it. But basically, the plate at the bottom has a area of very high velocity air that comes through around the spray nozzle, and that air is intended to pneumatically transport the particles up through that spray zone. And as the particles pass through the spray droplets contact the particles, and as they go up into the expansion chamber, the particles will decelerate so that they can fall back into the process on the outer edges. So once they fall back into that down bed region and the outer area, they basically are fluidized there. There's just enough air to keep them relatively suspended so that they're free to move about horizontally. And thus, when they get back to the bottom of the coating unit, the air in that outer bed, which is fluidizing them, will partition, some of it going up through that down bed and some of it basically being channeled to the up bed where they carry the particles and induce that circulation. So if you take a particle and time it through the process, it basically passes a full cycle about every 6 to 10 seconds. So depending on the length of a process, you can actually calculate approximately how many times it passes through the spray region. But it's this balance of airflow, and that is going to create the fluidization that we're attempting to obtain. So this is just sort of a summarize what I was just saying. Pneumatic transport up the center, particle suspension in the outer bed, or fluidization as we commonly call it. And then there's horizontal transport at the base, carrying particles into the up bed. And the balance of this air is dictated by particles. Any air coming into the outer bed, basically it depends upon the particle mass that's in the outer bed and the particle mass that is actually in the up bed region. That determines how the air will partition. So if you have a relatively lean bed, you'll get a different partitioning than you will with a very, very deep bed. And in addition, the partition height will influence how much the particles are gating into the up bed, and that will influence also that partitioning of the air. So what does it take to fluidize a particle? And this is pretty basic here, but if you go back, basically what we're counting on here is gravity to pull particles back down into the process. So we look at terminal settling velocities for particles. That ultimately will dictate what kind of airflow we need to suspend the particle. And in this case, I pulled information from the Handbook of Chemistry and Physics for 2 gram per cc specific gravity particles. And just briefly point out here the difference in the speed that a particle will reach. You know, in the absence of any air, basically they'd all fall at the same rate and continue to accelerate. But in the presence of air, it will reach a terminal velocity. So if we're looking at a 1,000 micron particle, if you were to drop that in the air and allow it to reach its terminal velocity, it would eventually get to 1,000 feet per minute that it would be dropping at. If you extend that down to something close to a 10 micron particle, that's only about 1 foot per minute terminal velocity rate for that. So basically, what we're doing when we're putting fluidizing air up through these particles, we're basically preventing that fall or stopping that fall, and we're just trying to suspend the particle. Now, we don't have air rates that are the same as the terminal settling velocities. They are substantially lower than that. And there are ways to estimate what that incipient fluidization velocity is. And by incipient, it's basically the base amount of air that would be needed to suspend a particle. Dr. Wurster had a book chapter in 1990 that basically presented the equation shown here, which came from a Woodcock paper that was put out in about 1953 or so. But basically, it's a means of calculating approximately what the minimum fluidization velocity would be for particles of a diameter less than 500 micron. So the graph there indicates those two things on the axes, the minimum fluidization velocity for the air and the particle diameter. Now, one thing, just to give you an idea of the difference here compared to the terminal settling velocity, if you look at the 2 gram per cc particle density or specific gravity, and you look at a 500 micron particle, you see that the minimum fluidization velocity required to suspend that particle is roughly 43 feet per minute air. And on the previous graph, basically the terminal settling velocity for a particle similar to that was somewhere in the neighborhood of 600 feet per minute. So it just roughly 15 times lower airflow required to just maintain suspension and for the process. Now, another means to determine minimum fluidization velocity is to actually put particles into a chamber. If you have put them in the chamber, you bring fluidizing air through the particle bed, and you can visually observe when those particles start to fluidize. And based on the amount of air you're putting through and the cross-sectional area of the bed, you can determine what the velocity of that air is that's inducing that fluidization. If you don't have a uniform fluidization plate, you can take a Wurster plate and you can basically set your partition up with 0 gap, so it's all the way down on the plate. Just tape off the top of the partition, put some particles in the outer bed, and increase the air until that outer bed starts to fluidize. Again, the cross-sectional area of the outer bed, so you can calculate what the air velocity is. But through the years, I've done some checking on various particles, and I came up with a table on the left. And the thing to take from this is basically you get down into the very low end of what's practical for Wurster coating. We're getting into below 15 feet per minute of airflow to suspend small particles, and that would actually extend down to 5 when you get into the very low end of what we do. And at the top end, if we were doing tablets, we might be in the neighborhood of 458 feet per minute air velocity. And so anyway, that tells us what we need in the outer bed to maintain the fluidization. So looking at this chamber diagram again, noted here, particle suspension requires somewhere in the neighborhood of 5 to 500 feet per minute air velocity. Now the pneumatic transport, I don't really have a good prediction of this. I basically have, again, extracted data from work that I have done and looked at what am I using for these various particles to actually transport it up through there. And I found that the air generally falls in roughly the 200 feet per minute range to 2,000 feet per minute range. 200 for a very small particle and 2,000 for something like a tablet, potentially. So this gives you an idea of what's needed on both sides of this, but what is really optimal in this? And I attempted to kind of quantify that in this next graph here. And what I'm looking at is what is the optimal, at least for coating place systems, what's the optimal up bed air velocity versus the down bed air velocity based on particle size, approximately. And I came up with this relationship. For working with a tablet, you're getting into a velocity differential of roughly 5 to 1. 5, the up bed is basically 5 times what's the velocity in the down bed. You get into a 2 millimeter bead, and it's more optimal around a 10 to 1 ratio. And when you get into very small particles, say 100 micron, you're talking about a 25 to 1 velocity differential. So this is what I would consider sort of the optimum we strive for, and will give us the most optimum processing conditions. One last thing, to bring up, here's a diagram again showing the downbed particle flow, the horizontal transfer and the pneumatic transfer up through the partition. One other thing that is very important is the particle trajectory coming into the upbed. We're basically counting on particles all the way from the outer edge of the chamber to basically pass up into that upbed. And if the upbed air velocity isn't sufficient, the particles can actually impinge early in the spray before it's fully developed. And this can lead to a lot of problems with agglomeration or perhaps nozzle capping, things that will interfere with the process. When you're running a process, quite commonly, we can't see what's going on inside the partition, only see the outer bed. Provided the outer bed is all fluidizing, we figure the process is fine and it will coat. But it's this trajectory of particles into the spray zone at the appropriate point is a real critical part of this process. Now, at University of Wisconsin work back in 1963, they put a shield or a collar around the nozzle to help physically prevent particles from getting into that spray zone. That was never carried through at Coating Place commercially. We tended to rely on optimal nozzle height for the positioning of the particles going into the spray, and also optimal air velocity to accommodate or optimize the process. Glad air techniques, they have patents back in the 1990s, I believe, that use a shield around the collar, and they're quite commonly used around the nozzle, and they are quite commonly used today. And I believe Vector in their system uses a protective sort of air current to prevent particle impingement on the spray. So that's all fine and good for a given coating unit. What I have here is just a diagram indicating the various sizes of coat chamber that we work with. We go down as low as a 2-inch, which doesn't really preserve an up and down bed. It's just random particle movement. When we move into the 4-inch and beyond, we actually have this up and down bed region that we work with. And if you look at the footprints, we go from a 4 to a 6 to a 9, a 12, and an 18-inch diameter in single nozzle units. The 18-inch diameter was determined in the university work to be an optimal size. And there's little advantage to going to a bigger diameter in a single nozzle unit. So for added capacity, we start nesting these 18-inch diameter units into a single housing. So at Coating Place, we do a 3-nozzle unit and a 7-nozzle unit. Now, in terms of linear scaling, when we go from an 18-inch to the 32 and the 46-inch unit, the 3 and the 7 nozzle, it's basically 3 times the airflow for the 3 nozzle and 7 times the airflow for the 7 nozzle. And that gives you an accurate scaling of the airflow. That is also consistent with the area of the plate. And the up and down bed air differentials are preserved in these scale ups. Now going down to the 4-inch diameter and forward, if we scale the airflow with the surface area of the plate, that is accurate, provided we preserve the air differential in the up and down bed. And that's the philosophy we use here. We basically have plates through this entire range that have the same air differential. And thus, when going from a 4-inch diameter chamber to a 6-inch, the airflow would be increased by a factor of 2.25, and so on down through the series here. And that scale up gives us or preserves the fluidization that we need for the process. So anyone who has a real interest in further treatises on fluidization principles, there are some pretty detailed books out there that cover this. Geldart was the author or the editor of a book in 1986 on gas fluidization technology, and Yang in 2003, Handbook of Fluidization and Fluid Particle Systems. So let's go on to the coating solution itself. Vehicle selection, we commonly use acetone and lower alcohols for processing, and water. This graph indicates the saturation point for these various solvents in air at various temperatures. Acetone has a higher vapor pressure, thus it's very high. The alcohols are somewhat similar, and the water is at the lower level. Now, we can't actually spray at these rates. We have to be cognizant of a lower explosive limit. So this following graph for the organic solvents, we look at the lower explosive, 25% of the lower explosive limit, which is a common goal, is to stay at a safe place. So we typically go no more than 25% of that LEL. But looking at this curve, if you look at 110 degrees Fahrenheit here, you see that you have about 0.34 grams per cubic foot of isopropanol would be at the LEL. So if we were spraying in a cubic foot of air that amount of material, we would reach the LEL. So how do we translate to fluidization air? Well, the fluidization air is 100 grams per minute. You multiply it by that 0.34 value, and it says 34 grams per minute would bring us to the LEL. So we stay within that limit. You know, we account for the solution solids to get a spray rate that would be appropriate for application. Now, that would be a maximum rate we could apply in a process. In actual practice, it depends on the coating system, the affinity of the coating system for the solvent, things like that, as to how effectively it evaporates. So it could possibly be below that level as well to get an optimal process. Moving on to water. Water, we don't have an explosive limit concern, but we do have a baseline water content that is basically indicated by the dew point of the air. So this graph shows the saturation curve for water, and it shows the water content at various dew points of 70, 60, and 40 degrees Fahrenheit. So what we commonly look at in practice is setting up a process with a spray that might take you to either a relative humidity value or a % of drying capacity. So when we look at relative humidity, if you look at 116 degrees or so, and you go up to the curve, we're right around 2 grams per cubic foot of water in the air. If we had a dew point of, or if we were looking for a relative humidity of 50%, it would be roughly half of that, or it would be 1 gram per cubic foot. So basically, we would bring up the spray from whatever dew point is, we bring it up to that value and preserve that humidity. Now, if we look at the % of drying capacity, we're looking at the difference between the dew point curve and the saturation curve, and spraying at a percentage of that value. So the following graph here basically subtracts off the dew point curves from the saturation curve at a variety of dew points. And this shows what the saturation point would be in terms of spray rate for the system. And then we would spray at a percentage of that and generally use that as a target for a process. And that generally gives us a robust process and condition. So nozzles are 2 fluid nozzles. Basically, there's a central path for fluid, hot melt, coating solution or suspension to pass through, and there's a concentric atomizing air channel. And basically, it's that volume and velocity of air in relation to the amount of fluid that is being atomized that determine how effectively the effect of the atomization is. One thing to be aware of on nozzles is not all nozzles are created equal. These channels are different. Some nozzles can have inherent pressure drops within the body itself. And so you can't always translate from one process an atomizing air and take it to another and say the same atomizing air is going to give the same performance. It's important to be aware of that. Droplet size is important because we're talking about drying here. And the more surface area we have, the more effectively we are able to dry things out. So this graph here basically shows if you double or half the droplet size, you basically double the surface area. If you decrease the droplet size by 1/3, you triple the area. and that leads to very fast drying, or much faster drying. Large droplets are generally a problem. They promote agglomeration. They can behave like core particles, where the material trying to coat actually coats the droplets, and as the droplet dries, it makes agglomerates. And large droplets do not generally track with airflow, so they have a mind of their own in what they do in a process, and that can create problems. So at Coating Place, we have a series of 5 nozzles we commonly use: CPI 6, 9, 12, a CPI number 2, and a number 26. These nozzles have been scaled linearly with plate diameter. So they scale with plate area. So 6 inches for a 6-inch plate, a 9 for a 9, a 12 for a 12. The number 2, which technically would be an 18 in our terminology here, but we haven't changed the name, is for an 18. And a 26 would be for higher. Now, we characterize all the nozzles at a height of roughly 100 to 120 millimeters above the nozzle tip. And that's a point where we're reasonably sure that the atomization has taken place. And that's where particles will start entering that plume. And so it gives us an idea of the consistency for the different scales. Now, looking at the number 2 nozzle, and its performance, we see here that we go from 110 to 520 grams per minute for these various curves here. The first 3 are basically the first darker curves, and the final 3, where the spray rate's getting higher, we start seeing the atomization basically fall off, and we're getting into larger droplets. But note that the D32 value, that's the surface weighted droplet size, we're generally down in the 7 range for the first 3, and we do have some change in atomizing air pressure there. But as we get up into the 300 grams, 400 and 500 gram per minute range, we get up to 80 psi, which is high as we can go, and we cannot get that same droplet size as we do at the lower spray rates. So I look at this and say, well, that's probably kind of where the optimum is below 200 or 250 grams a minute for that number 2 nozzle. And we commonly use it at higher spray rates for processes that the droplet size is not as critical. And the linearity I attempt to show here, I know I've got to give Jared some time in this talk, so I'm trying to be quick here, but basically, I look at the tip velocity as the way the nozzles were designed. And so at 50 feet per minute tip velocity, you can see the spray rate that would correspond to that. Those spray rates are basically linear scale ups to the plate area. So if I'm scaling from a 6 to a 9, I would go to 13.2 grams per minute from 5.9, and I would get similar atomization at that level. And these spray scale factors are equivalent to the plate scale factors, and so it allows for relatively simple scale up. Now, the next slide I have here basically shows the different scale of all the nozzles. So I linearly scaled them. On the right, you see a 25, 56, 101, 228, 476, and basically slight variations in atomizing air pressure, but in all cases, the surface weighted droplet size average is pretty consistent across all of these. So thus this simplifies scale up for us and helps us preserve the droplet size that we need as we scale. And put these into worksheets where we can specify what droplet size we want. We can scale a nozzle linearly, or we can scale the nozzle to whatever we need. But generally, we can get an atomizing air pressure that would give us the droplet size distribution that we want. So the final thing I'll leave you with is, I realize this was relatively quick, but when we talk about linear scale up, we're talking about going from smaller scale to larger scale. Smaller scale is not always fully optimized. So when we take those parameters and translate them, they probably wouldn't directly be optimized as well. And so there is some application and formulation knowledge that always has to be factored in when we scale up. So with that, I will pass this over to Jared. Thank you all.
Thank you, Chuck, and hello, everyone. I'm going to jump right in, talk about some particle size and engineering, and then I'll walk through some ways that coating can help with typical problems, and I'll finish up with a little more information about coating place. But for now, let's start with this perfect sphere. It's got a volume of 1 centimeter cubed and a surface area just under 5 centimeters squared. If I cut that sphere in half, I have the same volume, but in 2 pieces. But those 2 pieces combined now have about 26% more surface area than I started with. If I cut those 2 pieces into 4 and those 4 into 8, even though I end up with that same 1 centimeter cubed volume, I have now doubled the surface area that I started with originally. And this might seem like a simple idea, but it can be a hard concept to grasp. The particle size of the materials we're trying to coat have a significant impact on surface area and therefore the amount of coating they require. Now this should look somewhat familiar. It's similar to Chuck's plot on droplet size coming out of a nozzle. In this plot, we can see the range of particle sizes on that x-axis there that roughly cover about what we typically handle when we're fluid bed coating. And you can see there's a drastic difference between the surface areas of the same weight of 10 micron particles versus 10 millimeter particles. For reference, 1 kilo of a 2 millimeter particle has about the same surface area as a pool table. 1 kilo of a 14 micron particle is about the same surface area as a basketball court. If we wanted to apply enough coating to reach a 50 micron coating thickness, those 2 millimeter particles would need about 13% coat level. The 14 micron particles would need over 95% coat level. And if you're used to weight gain instead of coat level, what that means is your finished product will be composed of less than 5% of the core material we started with if we're using that 14 micron starting particle. Put simply, I know if someone gave me a paintbrush, I would rather paint the pool table than the basketball court. And remember, all of the theoretical numbers I've given so far are for perfect spheres. If the particle is anything other than that, the surface areas will be even higher. Now, this slide shows some benefits of small or large particle size. Smaller particles have less mouthfeel, which is important for orally dissolvable films, lozenges, and suspensions, so that we don't get that sandy mouthfeel texture. And we typically use a limit of 250 to 300 microns for those particles. The smaller particles tend to have more solubility, again, because of that increased surface area that we just discussed, and they're easier to suspend in a liquid. They tend to be less friable. For example, if we wanted to take particles onto a tablet compression process, we tend to see more success and less fracturing with smaller particles than large particles. However, large particles have their own benefits. They require less coating for an equivalent coating thickness, again, because of that smaller surface area that we just discussed. They have more efficient coating processes because they require more air to fluidize, which provides a higher drying capacity, which allows for a faster spray rate. And they, in general, they're a little easier to handle, larger particles than smaller. But we're not stuck with the particle size that we start with. If our drug is soluble, we can simply dissolve it and spray it onto a carrier particle. We often use sugar spheres or microcrystalline cellulose for this. In the same way, we can take a liquid drug and spray that onto an absorbent like porous silica or starch, and then continue treating that as a solid rather than a liquid. In the example on the top of this slide, the drug isn't soluble, but what we've done is apply it as a suspension onto that gray core particle. Each of those little blue drug particles is still discrete. That yellow layer can be something simple like a binding polymer, say hydroxypropylcellulose, or it could be some slow dissolving or eroding polymer matrix that will modify the release of the drug. Agglomeration, that's another option. If the drug is soluble, we could simply spray a neat solvent at some rate that encourages agglomeration, or we can apply a binding solution that encourages the particles to stick together. Now, this bottom example is a fun one. It's a special subset of granulation where we make a wet mass of the drug in microcrystalline cellulose, we extrude it, and that extrudate is placed in a piece of equipment creatively called a spherinizer. And what that spherinizer does is it breaks the extrudate down into shorter and shorter lengths until it's about as long as it is wide. And then the edges of that cylinder are rounded off to form a sphere. And we can take those spheres, throw them in a fluid bed, and just remove the excessive moisture. From there, any of these options can go on to additional coating or other processing, or maybe that's the finished dosage form. And we can, of course, make particles smaller too. We can use simple mechanical milling like a hammer mill or a conical mill. And if the particle isn't soluble, we can put it into a suspension and mix it under high shear or homogenize it, and then filter the solids out and dry them. If it is soluble, we can spray dry it or load it onto our choice of small particle. So now I'm going to switch gears a little bit and talk about some of my many problems. Most medicines taste terrible. Oftentimes we're working with drugs that are extremely bitter. We can apply a coating that masks the taste of the active but minimally delays the release. We can use things like starches, waxes, gelatin, gums, cellulosics, acrylic polymers, really anything that provides a temporary physical barrier between taste receptors and the drug. Additionally, we can include flavorings in the coating and also improve the surface texture for ease of swallowing if we're talking about something larger like a tablet. And that can be important for pediatric or geriatric populations. Now, if we have a drug particle that starts out looking like on the left and after a few days looks like what is on the right, we probably have a stability issue. The two biggest problems for stability of a solid oral dosage form are moisture and oxygen. A coating that's a good moisture barrier isn't necessarily a great oxygen barrier and vice versa. So we'll often use some combination of hydrophobic fats and waxes, starches, and cellulosics into single or multiple coatings. And because a well-balanced coating process can remove water as fast as it is applied, we can apply aqueous-based coatings to moisture-sensitive core materials without overwetting them. And of course, another potential source for stability issues is if we have multiple actives in the same dosage form that aren't playing well with one another. We can separate those actives out into different coatings or even place a barrier coating between them if necessary. Well, most of us have done it, and there are a lot of reasons for it, but missed doses can be a big problem in reducing the efficacy of a medication. So one of the things that we can do to improve compliance is to decrease the number of doses that patients have to remember to take. And we can accomplish this with extended release coating. Here, we're looking at a typical pharmacokinetic curve for a drug. The plot has three areas. On the bottom is a plasma concentration that doesn't do a whole lot of anything. There's that sweet spot in the middle where we get our therapeutic response, and then there's the excessive toxicity level on the top. This plot, this curve is an immediate release single dose. And when I take this dose, I get some therapeutic response in this area here. Now, if after that therapeutic response is done, I take another same size dose, look at what happens. My C max up here is now in the danger zone where we start seeing adverse events. Maybe I'll be in the market for a new liver or something even worse. But what if I had waited until a sufficient amount of that original dose had been eliminated before I take the second? Now, I can certainly do that, but now there's a big chunk of time where I'm not getting any benefit, any therapeutic benefit. And that can be important if this is something like a painkiller. The alternative is to apply an extended release coating. Now, often these are insoluble but semi-permeable polymer membranes like ethyl cellulose or cellulose acetate. They allow fluids to more slowly penetrate the particle, and the drug can slowly leach out. This allows for a higher dosage, that longer therapeutic effect, a lower C max. Look at the difference here, how much farther I am away from that toxic level. And back to my original problem, it allows for less frequent dosing. This is also a great way to avoid dosing at inconvenient times, like in the middle of the night. Now, we usually don't have the luxury of dosing our prototypes into people and drawing their blood for each and every formulation we make. So we use these in vitro dissolution tests instead. And this plot shows the difference in dissolution rate for the same immediate and extended release dosages that I just showed. Now, there are several reasons one may want to target delivery in a specific area of the gastrointestinal tract. We might want to keep a drug from releasing in the stomach because it could cause stomach discomfort to the patient, or the acidic conditions there could degrade the drug itself. Targeting a specific area of the gut can allow us to deliver more of the payload to that area where the drug is most bioavailable or needed the most. And that can also lead to allowing us to use a lower dose because less will be released in the non-target areas. But you ask, we just went through the benefits of an extended release coating, so why not just extend the release out to that area where we want the drug? Well, one reason is that we're going to have some amount of drug release prior to when we get to the target. Another reason is this table here. These data show just how variable digestion can be. In this study, 20 volunteers swallowed special capsules that recorded pH and allowed the researchers to determine over time where they were in the gut. As you can see, there's a huge range in these transit times. Now, keep in mind that the feeding schedules of these volunteers were kept similar, so we would expect to see even more variation in the general population. We could give the same 2-hour extended release medication to this person, and they might have 100% release in the stomach. Well, this person doesn't have full release until it reaches the colon. Lucky for us, the gut has some built-in pH gradients that we can use to our advantage. Incidentally, just like transit time is very variable, so is pH. You will be hard-pressed to find two diagrams like this that agree with one another. This is my version. One of the more common means to achieve the delayed release is through enteric coating, where we keep the payload intact through the stomach and then release somewhere in the intestines. And enteric coatings we use are weak acid polymers that are resistant to the acidic conditions of the stomach, but then dissolve at a higher pH. Most of the commercial enteric coatings on the market contain one of the ingredients in this table. They usually deliver drugs to the small intestine, but combinations of enteric and extended release coatings can consistently deliver drugs even to the large intestine. And this is what that looks like as a dissolution curve. And if we apply an enteric coating over the top of a extended release coating, we get something that looks like this. Bonus, switching from solid dosage to liquid dosage. Liquid formulas can be desirable because some patients don't do well with trying to swallow tablets or capsules, and it's also easier to adjust a dosage with a liquid. We can just measure out a different volume, say, rather than try to cut a tablet in half. However, it's difficult to have anything other than immediate release from a particle in a suspension. All coatings, at least the ones that are approved for human consumption, are going to have some amount of leakage over time while they're in a liquid. One answer to this is to use an ion exchange resin. Coating Place worked with Penwalt Corporation to advance the use of ion resins in controlled release way back in the 70s and early 80s. In the example I'm showing here, we're taking a basic drug, dissolving it in water, and then we suspend this insoluble cation exchange resin in the drug solution. That's the big gray blob there. The surface of the resin and the active are attracted and ionically bind together, and the counter ions form a salt. Now the loaded resin can be dewatered by filtration or centrifuge and then dried in a fluid bed. That resin can then be used as is. It can be combined with other excipients to make a dry, reconstitutable suspension, or it can be made into a controlled release aqueous suspension. As long as there are no competing ions in the liquid, the active will remain bound to the resin. There are several options for both strong and weak resins on the market for both acidic and basic drugs. As long as the drug is ionizable, there's a chance it will have an affinity for one of those resins. Ion resin complexes naturally taste mask actives, and they can also extend release of that active depending on the strength of the resin and the affinity for that drug. Additional extended release coating can also be added to prolong the release even longer. And ion resins are yet another way to minimize particle size and increase bioavailability, because these resins are often under 150 microns or so. So now that I'm nearing the end of my presentation, I need to point out that Coating Place can provide all of these services that I've talked about and more. Oradel is our line of oral delivery platforms that can remedy the problems that I just talked about. They are not a one-size-fits-all coating formula. We do not charge licensing fees for them. We are offering a set of technologies and formulation expertise. And I just want to point out that schematic on the right is actually representative of our multi-layer coating ability. It's a graphic of a product that we have helped develop. It had a couple of different actives loaded onto a carrier particle, multiple barrier coats, extended and delayed release coatings. So the examples that I just went through are relatively simple, but I wanted to show that formulas can get a lot more complex than that. And here's a little more information about Coating Place. I'm running late, so I will not read this to you, but I encourage you, if you have any more interest in Wurster coating or Coating Place, please check out our website. I'll turn it over to Sonia.
Well, thank you very much, Jared and Chuck, for that very insightful and detailed presentation. I hope everyone enjoyed it. Before we begin the Q&A portion of the webinar, I have one last quick poll question to launch, and I'm going to do that right now. So audience members, you'll see it in front of you. So please, I encourage you to go ahead and cast your vote. This is multiple, so select all that apply. What coating or control release options interest you? And as I said before, select all that apply. We have stability improvement, taste masking, extended release, enteric delayed release, ion exchange resin technology. I'll give you a few more seconds for you to complete this poll question, and then I will close the polls, share the results, and we'll begin a quick round of the Q&A portion of the webinar. Okay, perfect. That looks like we got the majority of our audience members engaged in that poll question. I'll give a few more seconds, and then I will close it and share the results. Okay, I'm going to close it now and share the results. Okay, so for that question, what coating or control release options interest you? We have 47% saying stability improvement, 41% saying taste masking, 35% saying extended release, 47% again for enteric delayed release, and 41% for ion exchange resin technology. So thank you everyone for participating in that last poll question. Now we're going to begin the Q&A portion of the webinar. I know we have a bunch of questions that have come in, so we're going to try to do our best to get at least one or two of them done. I will encourage Chuck and Jared to put on your webcams now. Hi, everyone. Okay, there we are. Okay, and let's do this round, this fast-paced question round. So let me just get to the first question here. Okay, and the first question is, let's see here. Does optimizing nozzle air pressure affect the the coating process? If yes, why and how?
I'll answer that one.
Okay,
atomizing air pressure is a tricky thing. The higher the atomizing air pressure, the more energy you put into the system, and it tends to beat up particles. So there has to be a happy medium in some cases. And coat solution, its viscosity will influence how much atomizing air pressure you need to get a given level of atomization. What I find is you have this balance between the viscosity and perhaps an atomizing air pressure where you are getting adequate atomization without beating up the particles. And yeah, there is definitely a consideration there. And you have to account for that potential to beat up particles too much. So I don't know if that answers the question, but it is a tricky thing.
No problem. Here, let me just squeeze in another question as we're down to only 2 minutes left. We have a ton of questions from our audience members, so sorry. Well, this will be our last question. And the question is, the dissolution from ion resins depends on quaternary concentration. How to standardize drug release in vivo from them?
Well, a lot of that, again, depends on the strength of the resin and how much it's attracted to the drug. So keeping the electrolytes and the counter ions in the stomach consistent through fed or fasted conditions can be important. There have been some studies showing that ion resins actually level that out, so you don't have to worry as much about fed or fasted conditions. So they can be very reproducible without having to worry about that. So I'm not sure. I'm also not sure if I answered that question, but that's the best I can do with that information.
Okay. All right. I'm going to squeeze in one more question.
If someone wants to email.
Yeah, that would be perfect. Okay, here's our last question. How can I determine the velocity differential for a fluidization plate?
Yeah, what you need is some information about the plate itself, what its porosity is in the two regions, the up and down bed. And what I commonly do is look at the percentage of air that goes to each of those regions divided by the percentage of the area that represents, and then normalize those values. And basically from that, you can get what that velocity differential is. But if you look at, it comes down to how much air is going through each region, and you know the square footage in that region, so therefore you can figure out what the velocity would be. and figure out what the differential is.
Okay. Well, thank you very much, Chuck and Jared, for answering those questions really quickly. Well, thank you very much for those questions. We have reached the end of the question and answer portion of the webinar. If we couldn't attend to your questions, the team at Coding Place will follow up with you after this presentation. Now, if you have any further questions, please direct them to the email address that's on your screen, and there it is, info@codingplace.com. Thank you everyone for participating in today's webinar. You will be receiving a follow-up email from X-Talks with access to the recorded archive for this event. A survey window will be popping up on your screen. Your participation is appreciated as it will help us to improve on our further webinars. Now, I'm about to send you a link in your chat box. You'll be able to view the recording of this event at that link and also share this link with your colleagues when they register for the recording as well. So I encourage you to do that. And get even more out of today's presentation by downloading the supporting materials available under the Handouts tab. And we have 3 there for you: Coding Place Company Information, CPI Wurster Fluid Bed Processing Scaling, and Premature Release from Wurster Fluid Bed Enteric Coatings. So there you go. Please go ahead and check them out. Now, please join us in thanking our speakers, Chuck and Jared, for that very insightful presentation. So thank you very much, gentlemen.
Thank you all for your attention.
Thank you. We hope you found this webinar informative. It has been my pleasure to be your webinar moderator. On behalf of the team here at X-Talks, we thank you for joining us. I'm Sonia Hunt. Until next time, please take care and bye for now. Bye, everyone. Thank you, Chuck. Thank you, Jared. Bye.
Bye.
Bye.